All right. So just to quickly recap, we have talked at length last time what happens when I'm trying to store integer into a computer. And the biggest problem we're facing is that we have finite memory to do so. And we also have to figure out what are the rules going to be, how am I storing that integer into the memory. So in essence, our computers work on this 0-1 world. They don't have 10 figures to assign what numbers are to other computers. They only have on and off switch. So they work in what we are calling base 2. The only digits in base 2 are 0 and 1. In our world with 10 different digits, we have digits 0 to 9. And we are so used to thinking in terms of tens that we don't even, that's how we internalize and understand numbers. We don't even think that that could possibly be different. If we had 8 fingers, we would have a different row. Okay, so how do we switch back and forth? Because ultimately I have to somehow fit those numbers into computer memory. So first thing is we have to figure out how do I basically switch back and forth. And we go back to actually how we do decimal numbers. Okay? When we say number 25, it's 2 tenths, which is a power of 10, plus 5 times 1, which is the simplest power of them all, 0 of 10 as well. And basically, every time I'm trying to represent a number, I try to fit as many of the large ones that I can, and then I just look at the remainder and repeat the same process until I'm done with the number. We're going to do the same with base 2. So if I had 25, okay, the largest power of 2 I can fit in there is 16, one of those. And then I could really have 0, 1 in the world in base 2. And then I can fit an 8 and then a 1. Okay. I do represent all of the missing powers in the range. I put a 0 in there, just like I would for a number 205, right? There would be 2 times 100 plus 0 times the 10 plus 5 times the 1. So same I do in the base 2. So I'm going to actually have that 25 is 11001. So this is my 2 to the 0. This is 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. Right? And this is my representation in the binary world. And next step is understanding that computer memory is divided in these bytes, which are one word is 8 bits, which is 1 byte. So then I have to figure out, okay, how many bytes am I going to have for this number, integer, and then fill in any leftover space with zeros. Okay, so if I had 2 bytes and 173, which is given like this, basically I would put in all of these numbers here that I found while converting the number, and then fill in with zeros. I also have to figure out whether I want to store signed integers or unsigned integers. And if I want negative numbers to be reality as well, then I have to reserve one spot for signed. So it's a lot of bookkeeping, but again, computers don't know anything until we tell them, so we have to figure out what those rules are. Or somebody has figured out, we're just now learning what agreement is. Yeah? So basically in that case, I then have, if I reserve one spot for the sign, then the leftover is what I have for the magnitude of the number. And what that magnitude is depends on how many spots I have, and that determines the largest and the smallest numbers that I can store in there. There's only one other quirk for negative numbers, right? So basically, if I had only positive numbers, 0 is always my smallest one, great. And all the others I can fill in with the magnitude, so I just throw in ones and figure out what's the largest number I can put in there. So if it's 1 byte, it's from 0 to 255. However, if one of those bits is reserved for a sign, then technically I have a positive 0 and a negative 0, which mathematically is a waste, right? Because both are 0. So one of them is by agreement mapped to one more number so I can expand my range. So in case of positive and negative numbers, if I want to store them in 1 byte, I can go from minus 128 to 127. So the actual number of numbers is the same as 0 to 255, it's just shifted. And I could repeat the same for as many bytes you tell me that I have for one integer. I do have to know whether it's assigned or not. And typically we go with 1 byte, 2 bytes, 4 bytes, and rarely we go above that. Okay. So that's the most common. All right, so now that you know that, then it's going to make sense that, so for a 2 byte number, if I have 2 bytes, I can go for either from 0 to 65,000 or so. Where's the number? I don't recall what the number is, but it's 65535. Okay, so my 2 byte number can either be 0 to 65535 or negative half-ish of that to positive half of that. Okay? So basically that's the range here that is stated over here. So if I can have those numbers as negative, then they go from minus 32,768 to plus that. Okay? So given that, can you actually store 4 million in either a 1 byte integer or 2 byte integer? Is 4 million larger than 65,935? So if I'm reserving only 2 bytes for integers, I cannot store 4 million. Can I store 32,767? Let's write that maximum that I can store. Can I store negative 3,290? A little bit over, right, in magnitude. So no, I cannot, not in 2 byte integers. 60,000? If I have unsigned or positive 2 byte integer, can I store 60,000? I can't. It's less than 65,535. If it's signed 2 byte integer, can I store 60,000? So I have to know what I have in memory. Does that make sense? I have to know how is this memory designated for storing numbers. And I have to know what is stored in there before I read it in correctly. Now we have real numbers. And for real numbers, we first decided to, okay, we have to come up with the rules. And those rules have to be consistently applied, otherwise there will be a failure. So first things first, we're going to use scientific notation to normalize the number. Okay? So 37.5 is something larger than 1 times 10 to the power of something. Okay? So I have what we call mantissa and exponent in there. And similarly, I could go for very small numbers. Now, technically, and I'm not going to ask you to do this exercise, I just want you to understand what the steps are and where the errors are and why you can't be as precise as you'd like to be often. So basically, then I can convert that also into a power of 2 and powers of 2 as opposed to powers of 10 because computers don't work in terms of powers of 10. And by agreement, we convert this as 1 plus, since I have to be larger than 1, it's 1 plus some mantissa p times 2 to the power of t. And we call p a mantissa and t an exponent. And then now, basically, I'm dividing the space that I have reserved for this number to storing mantissa and storing exponent. So computers come in and they will read the mantissa part and read the exponent part, and then they'll convert things before storing them, and then convert them back before presenting a number to you. And in that process, I would have errors. So basically, if I had a 32-bit number, then I would have 24 bits for P and 8 for T, including a sign. And if I had a 64-bit number, I would have 53 bits for P and 11 for T. And this is where basically limits come into play. So basically, if I had what we call a single precision number, which is 32 bits, then basically I can go up to 10 to the 38. Okay, those are my largest numbers. And as low as 10 to the minus 38. So around 0, there are certain numbers that are way too small for me to store, because they're 10 to the minus 400, for instance, okay? If I had single precision number. So I can store 0, as long as I zero everything out, right? But then there's like a bunch of small numbers I simply cannot store. That's called underflow. Then my minimum starts, and in single precision, minimum is around 10 to the minus 38. And in double precision, which is 64 bits, I can go smaller, but I'm still limited. My minimum is 10 to the minus 308. And then the numbers that I can store start up to a maximum. Okay? And I, at some point, don't have space for very large exponents. Also, in between, I'm a little speckled. Okay? Because I have limited space for so these are exponents. I have also limited space for those mantissas, P. So there's only so many digits that I can store. So let's just see, and I'm going to break this down. I want you just to understand why you actually have gaps in representation. So we're going to see how it looks like in a very, very simple world. And that world will be that of just having a single spot. And we're going to work with basically, let me just enlarge this a little more. So we're going to work in the world of having only space for 1 digits, and we're going to just work in digital world. I'm not going to go to binary, just to represent what these limitations are. So let's assume, so this is a simple example. And this is, whoa, hi. This is where my computer decided not to react. All right, I'll have to go to simple example on paper. I apologize. For some reason it works with the mouse but not with the, need to reboot my computer. Okay, pause.